Alright, so last I worked on, I got to a dead end because I was trying to pre-compute the beautiful numbers based on pure logic, and um, I got to, I think, to like 6 digits, but then the 7 digits, which were necessary for the full um, possible set of inputs, was let's say more difficult than what I could realistically kind of do manually. There was just a lot of combinations there, which led me to reconsider like what the hell I was doing. So after thinking about it and sleeping over it, what I ended up thinking about was the fact that pre-computing as a general principle is fine in this instance. I probably mistakenly had like a belief that I needed to either just do pre-compute completely or do a kind of on-the-fly answer completely, one or the other. But I thought maybe, yeah, I just need to actually create the full list rather than try to logically determine what the one next highest value would be. So that's the approach here. Basically, completing the full list of all possible beautiful numbers and then finding the next highest based on that list, rather than just doing like, given this n value, try to find the one next beautiful number based on logic. So and there's a couple of different kind of other techniques here, but first up is for every digit length, coming up with the possible combinations of digits that would combine to that digit length. I called those combos, which was something similar before. So for instance, a combo could be for one digit just 1 1. For 2 digits it's just 2. For 3 digits it's 1s and 2s or 3. For 4 digits 1 and 3 or 4. So these are the combos I was thinking of, but again I need to just create these. I think I guess I didn't need to create this on using code, but because it's still pretty finite in terms of what combos could make anything up to 7 digits. But here's the code way for combos up to kind of an arbitrary number of size. And I guess if you had digits where the base of the number system was also kind of arbitrary, then this would work, I guess. But so a combo is going to be here a list rather than a tuple, but so it's going to be recursive. There's going to be a last digit, which initially is called with 0, or yeah, last digit. The digits is which is an array, and size, which is the remaining number of digits, I think. The remaining, yeah, number of digits within the combination. So if there's some last digit, let's say the last digit is 0, so you can start with 1. If the last digit is 2, then the next digit has to be 3. So it has to be 1 bigger than the previous last digit that was placed in this combination. You append that to your array of digits. You check what the remaining size is, because if you place a digit that's 3 into your combination, then that means you remove 3 size from the overall size of this thing. And if you have 0 left, then this is a valid combination. If the size initially is 6, and you place a 1, a 2, and a 3, and size is now, or the remaining size is now 0, then 1, 2, 3 is a valid combination. So add those to the combos being kind of a overall list of all those other lists, all those combination lists. If the remaining number of digits, or remaining spots is greater than 0, but less than what you just put in. So if I put in a 3 and there's only 2 spots remaining, then technically the next thing I need to put in is a 4, but then that's just too little. If the remaining thing is more than what I just put in. So if I just put in 3, there needs to be 4 spots remaining. If I just put in a 2, there needs to be at least 3 spots remaining. So if that's the case, then go ahead and do the recursion where it goes I is the last digit that's been placed, digits is the just digits array, and the size is now reduced by how many digits was taken up by I. And then just so that iterates recursively, dives into it, and then after you're done with this, adding this value of I, you pop it. In any case, combinations should work in terms of, let's go and just run this thing. So combinations should, if I go through 1 through 8, why didn't combos print out anything? Print combos. Oh, that's right. I think I need to make there's some other code that kind of prevents it. Actually, maybe let's just comment this way. Comment this out for the moment. So combinations here, this is all the possible combinations. So it could be 1 for 1 for 2 digits, or for size 2 it's going to be just 2's. Size 3 is going to be 1's and 2's and 3's. Size 4's is going to be 1, 3, or 4, so on and so forth. I wonder, this makes me think that maybe I could have done something else. Because overall this is pretty unorganized. In any case, or there's some other logic that could work, that could have worked here. In any case, so that was the combinations. The next thing up was creating all possible beautiful numbers. So this is all possible beautiful numbers from every combination. So for instance, if I have a combination that is 1, 4, or maybe let's say 2, 3, so this is going to be a 5-digit number. So 2, 3 is the combination. I'm going to create a frequency table or frequency dictionary mapping where I'll say 2 has 2 frequency and 3 has 3 frequency. And obviously I'll have a total number of digits that I also just keep track of here. So for each digit, this just creates the mapping. And then I'm going to have a function makeBeautiful, which uses this current frequency to create an array of all possible beautiful numbers from that frequency. So makeBeautiful, even though it doesn't have that as a parameter, it does use this digit frequency. Maybe I should pass that digit frequency just to be clear, because it otherwise would. Yeah, it's fine. Even though that is technically just using this resetted frequency table each time. So left is how many digits are left, and this is also recursive. So if there's no digits left, then it's going to convert this order of digits to an actual value that's this order of digits being an array of digits, it's going to convert that to an actual value, like a integer, a single integer. So it just multiplies each place in the order with some increasing power of 10. So yeah, its value is initially 0 for each kind of place value, where the place value has capped as the length of the order. It's going to increase value by power of 10 times the digit. Order is the order of digits, and then append that beautiful value to the beauties array and return. So that's the base case. Recursive case is it's going to go through each digit and digit frequency. As long as the digit frequency is not 0, then it's going to append to the order the digit. It's going to decrease the frequency of that digit. Does the recursive call, passing in the frequency, the array of digits, and saying that it's one less digit. After the recursion, then it's going to reset it, so it's going to take out that last digit that was placed and then put back the digit frequency. And that's just the recursion for Make Beautiful. And just to be clear here, Make Beautiful is meant to, and then it sorts it, because I don't want to figure out the order of things. Let's go return 0 here. So then it gives everything here. This includes up to 7 digits, because I made combinations up to that being the highest thing possible with the parameter space. But here, one thing that I did do was I just used this code to compute the statics that I had before, the static list of digits we had before, and I made a pre-compute beauties array, and these are all things up to 6 digits. So the 7 digits, which is probably the same size as, or same size or maybe bigger than the first 6 digit, all the things that are 7 digits that could be a beautiful number, that I left to be pre-computed or computed on the fly or within each call. So let me go and just say that the pre-computed beauties are 6 digits. 6-digit beautiful numbers are pre-computed. 7-digit numbers will be computed each time. Each call. So if it's a n value where the n value is less than the highest 6-digit pre-computed beauty number, then I'll just return the correct beautiful number for that n call. So I use bisect left, or sorry, bisect right. Bisect right meaning that it would find the index of the value in a sorted list, where if there's a tie, it'll go to the index after it rather than the index of it. So if the number is exactly 22, it'll give me the index that is 0, 1, 2 rather than 1. If I do bisect left, it'll be 1. And by the way that this question is asked, is find the next beautiful number rather than the beautiful number that is kind of equal to or higher. Equal to or higher, it's just strictly higher. So bisect right, and then return that. Otherwise, it's going to create the combination and create the beautiful numbers based on knowing that it's going to be like at least 7 digits or 7 digits for the beautiful number. So it does that, creates all the. So at this point, maybe I don't need the full code for combinations because I could even pre-compute the combinations or whatever. And then, yeah. So it's going to do 7-digit beautiful number sorted, bisect right at that, and then return. And I think this should be pretty fast. I think it's random. Sometimes it gives me 0, and sometimes it gives me whatever that is. 3 milliseconds. Okay. Anyways, so none of this was needed, or this is owed work from last time. So summary here was in general, rather than determining the next beautiful number, the single next beautiful number, calculate or generate a list of all beautiful numbers and search, which is the binary search, for the next beautiful number within that list. So to decompose the generation of the beautiful list, one, find all combinations for each length of number, so which is i.e. the number of digits. Find all combinations of digits that would combine to that length. So that was this make combination for every combination from 1 to 7 inclusive. Yeah. Here I used a recursive function to do that. I think that might have been one of the harder parts, maybe kind of on par with the difficulty of actually the make beautiful function. But yeah. And then for each combination, generate a dictionary of digit to frequency. So example, 2 digits to 2 frequency, 3 digits 3 frequency for a 5 total digit value. Use a recursive function that to generate all possible orders with that, or unique orders with those digits, and add the beautiful number and all possible unique orders with those digits. Convert order of digits to integer value. So like if it's 2322 or 23332, then it converts to 23,332. So like 2, 3, example, 23332 converts to 23332. And add value to beautiful list. And then lastly, sort list, find search using bisect right. For n in list and return appropriate value from list. And then extra, this is just for extra optimization. Recompute the small value list. So let's say digits is less than or equal to 6. Small beautiful value. And return from that list if n is less than the max of that list. Otherwise, compute the beautiful, or the 7-digit beautiful numbers list and return based on that. This is very optimized, very sensitive to actual parameters, I say constraints. Stated could be made more generic. So this definitely relies on the fact that they're telling you n is up to 10 to the 6, so that means 7 digits. This was more bigger. I mean, I guess it can't be that much bigger because base 10 has only 9 digits, right? Or only 9 is the biggest 1-digit value, so it can't be much bigger than that. But in theory, it could be more if there's a base system that was like base 16 with hexadecimal or something. Time complexity. This is pretty darn. I wouldn't say it's constant. In some ways, it is constant. Well, I guess if in some ways this is constant, as the total work done is kind of proportional to the number system, the kind of number of digits, and since that is fixed, then there is a cap to how much work needs. Well, there's a cap to the work needed, or the time needed. So I guess, yeah. But if the number system did have a variable number of digits, let's say d, then it'd be like d of d squared, maybe. Be akin to d squared, I think. Roughly. Because I think that would be the number of tuples necessary, or the number of combinations. number combinations. Yeah. Okay. Space complexity. This is gonna be O of D. Since arrays for orders, actually, since arrays for combinations. Actually, combinations is like D squared, isn't it? Of D squared since combinations and orders of digits. Orders of digits will take some space. Combinations is not that much space, but there's some space. Yeah. Okay, I think that's a wrap. To pre-compute the beauties. Recursion. This is recursion that's kind of backtracking, I think. Yeah, I think this is backtracking. Because you try something and then you backtrack out of it. Yeah, backtracking recursion. What's this? Yeah, it's combinations. Yeah, this definitely could have been pre-computed the combinations as well, which makes a lot of sense if I were to have given that more thought. Okay. I wonder if this is random.